If you haven't heard about Anchor, it's the easiest way to make a podcast. Let me explain. It's free. There's creation tools that allow you to record and edit your podcast right from your phone or computer. Anchor will distribute your podcast for you so it can be heard on Spotify, Apple Podcasts, and many more. You can make money from your podcast with no minimum listenership. It's everything you need to make a podcast in one place. Download the free Anchor app or go to anchor.fm to get started. Welcome to the new Chemist. We're glad you're listening. Feel free to download this podcast on Google Podcasts, Apple Podcasts, and other platforms. Here on the new Chemist, we discuss chemistry, which simply put is the science of change, as well as careers, community, research, and COVID-19. We're happy you're tuning in. My guest today is Stanna Dorn. Thanks for joining me today. It is so good to hear from you. Just briefly, I'll inform my audience about you. Stanna Dorn is from Grayling, Michigan. She graduated with a BS in chemistry and a BA in music from Hope College in May of 2017, where she performed research under the guidance of Dr. Jeffrey B. Johnson. This involved the development of a rhodium-catalyzed cross-coupling reaction, resulting in the interconversion of quinolyl ketones. In the Brown lab, Stanna is currently working on the elaboration of alkenes via copper-palladium synergistic catalysis. When she's not in lab, Stanna enjoys reading, playing the flute, singing, creative writing, playing volleyball, and kickboxing. Please welcome Stanna Dorn. Thanks, Stanna, for joining me today. It is good to have you on.
Thanks for having me.
Yeah, so Stan is actually one of my mentors, one of my former mentors in the graduate program. So it's really good to have on as a guest. So Stan, as we begin, what have been your long-standing interests in the field of science?
That's a great question. Starting off as a younger kid pre-college, I didn't know what organic chemistry was, and I was fascinated by chemistry in general, and so that led me to pursue a chemistry degree at Hope College, and through there, I first started off doing analytical research. But as soon as I took an organic laboratory course, I fell in love with organic chemistry. I think putting together molecules and thinking about how to put them together and strategies for doing so is extremely fascinating and rewarding.
Okay, good. So would you say you lean more towards synthesis, or do you lean more towards theory, methodology, or
Ooh, that's
applied
a good
organic
question.
chemistry?
Yeah, so during my undergrad, when I started organic chemistry research, I started off by doing organometallic research
Okay,
using rhodium chemistry.
okay.
And this was extremely interesting to me. I hadn't quite taken inorganic chemistry yet, so I didn't quite know how metals worked and everything, but I thought it was super interesting. And I also got to use the glove box, which was exciting. But
Oh wow. In undergrad,
in
you used the
grad
glove box?
school, yeah,
Wow,
yep,
that's cool.
yeah, we were fortunate enough to have a nice one at Hope College, so that
Yeah.
was super fun.
Good.
But yeah, then in graduate school, I definitely at least wanted to start off doing organometallic research because that's at least something that I had a partial background in. And I thought I could build more upon those skills in graduate school. And so that in part led me to Kevin's group. And once I found out I was working on the dual catalytic system with copper and palladium, I was super excited because I'd never seen two intersecting catalytic cycles for metals before. And I was super intrigued by it. And
Okay.
yeah,
That's good. That's
I
good.
definitely have an appreciation for synthesis. And I haven't had the opportunity yet to do too much work in that, but I do find it interesting as well.
That's good. That's good. So, given the challenges that a lot of people are facing, and you may have faced some challenges as well, how do you maintain a view of the bigger picture in your career, graduate career, and in your life in general?
Yeah, this is an excellent question. And a lot of people that I meet in graduate school are sometimes surprised to hear that I actually did not do well in my organic lecture courses as an undergrad. I almost failed them.
Oh, wow.
And but I did really well in the lab. And going through that process, I remember feeling extremely frustrated because I didn't seem to pick up a subject that I loved to death as much as my classmates could. And
Okay.
so the passion that I had for it just really wasn't translating into, what traditional measures are for learning. And I remember being extremely frustrated at the time. Um, and going beyond that, once I fell in love with lab work, I was like, I'm just going to pursue organic research and see where it gets me. And through that, I started organic chemistry research. And there were definitely times I felt insecure because I didn't do well in the lecture course. So um, I definitely sometimes felt like an imposter, which a lot of people experience, especially in graduate school, is that imposter syndrome.
Hmm.
But kind of through it all, I've been extremely passionate and excited about pursuing a career in academia, and keeping in mind the struggles that I faced as an organic student and how I can help students who maybe, were in my situation, help understand it better. Because especially at organic chemistry, we tend to see a drop off of students because it's the weed out course and it's extremely hard and it has all these stereotypes for being a really tough course that is unforgiving. But so I think we lose a lot of students there, and I'd like to help bring more people in.
Okay, that's good. That's good. So, Stanley, you mentioned a lot of stuff, and I want to touch on a few of those things. So, how did you work through that imposter syndrome? How did you work through? Because
Oh,
a number of people face that.
um, yeah. To be honest, I'm still working through it.
Okay.
And I'm not sure there's ever going to be a point where I wake up and just it's magically gone. But
Okay.
I try to remind myself of the things that I have accomplished and um, kind of the power of the word and. So I can be a successful scientist and feel insecure at times about where I'm at. But that
Okay.
doesn't mean I'm not successful, and it doesn't mean that I don't belong here.
Hmm.
Um, and
Wow.
um,
That's good. That's good. It's good because, many times we have these ideas of grandeur where scientists are concerned, where we seem to be strong, completely, have their life perfectly lined up. But many times that's
yeah,
not the
for sure.
case. Yeah.
Oh,
So
I would say majority of the time that's not the case.
yeah, that's true.
Um,
True. That's true.
but
Yeah.
yeah, as scientists, sometimes, um, regardless of what scientific field you're in, or maybe regardless of fields um, specific to science or not, the higher up you go in terms of like education and things like that, the more pressure there is to know um, all of the deepest theories of the subject. And just with organic chemistry in particular, there's the pressure to like know all the named reactions that ever were and ever are, um, and things like that. Um, that at times, can feel excluding, um, especially as a student. If you get kind of mocked for not knowing a named reaction, it can be really off-putting when maybe you still at least understand the underlying concepts.
Okay.
I'm not
Yeah.
trying to I'm not trying to rail against named reactions. It's useful to have monikers to describe these processes. Um, but I do think that sometimes it goes a little bit far.
Okay. Yeah, that's good. So, Stana, I have a quick question. Another
Yeah.
question. How have you been adaptive and creative in the field of science?
Ooh,
Or how
that's a
or how have you carried someone or fulfilled the creative ideas of another person? Because typically in grad school we don't come up with our own ideas. So
yeah, definitely not at least at the start.
yeah.
I you know I think in terms of graduate school and working on projects and um, just in general, science or not, curiosity is a really great thing to have and to pursue. And that leads to always asking questions and thinking deeply about, especially what system and processes you are studying. Um, and so even if, you know, especially at the beginning of grad school, you're oftentimes given a project that someone has already kind of thought out the main idea. But just because that main idea is thought out doesn't mean you can't contribute something to it by thinking more about the finer parts of the project and asking
Mhm.
the questions like, can we take it in this direction? What if we try this? Or could we adapt the system to XYZ? And, it's not, especially as a younger student,
Mhm.
um, it's not always going to be. There's been times where I'm like, why don't we do this? And Kevin's like, meh. Um, and so, but that doesn't mean you stop trying to come up with ideas and ways to push the project forward. I think that kind of curiosity and persistence are really what drives science.
Okay, that's good. So, I would say, would you say you found the right environment for you to thrive scientifically and intellectually?
Um, I do.
Okay,
Um,
so how did you find
I
it?
my pause was thinking about answering for both undergrad and graduate school, which the answer is yes for both.
Okay.
Um, I chose my undergrad institution, Hope College, because it's well known for its chemistry program, and that's one of the areas I was interested in at the time. And I remember my first summer of research, I was in an analytical chemistry group,
Okay.
but we would go to these seminars and stuff, and I would see this other group that was organic chemistry, and they always seemed like they were an amazing community and just having fun. And I was like, I want to be a part of that.
Okay.
Um, so that's how I ended up in my undergrad lab. And
Okay.
then when picking a grad school, it was really tough for me. Um, and one of the reasons it's a tough decision is because oftentimes there's more than one good option, and there's no way to know which one is the better or if there is a better option.
Mhm.
Um, but I talked a lot with Kevin when I was deciding about graduate schools, and through those conversations, I got a sense of how supportive he is for the group and for our careers beyond the group.
Mhm.
And that to me was more important than any research area I worked on,
Hmm.
was having a positive group environment.
Yeah, that's true. Because a toxic group environment, I don't think is conducive to progress. I don't think so. Yeah.
Yeah, especially, for underrepresented people, it's
Mhm.
that's how we drive people out.
Mhm. Yeah, I agree. So, how do you maintain a balanced life, given all your responsibilities and accomplishments, winning awards, doing research, good graduate student? How do you maintain balance with all these things, all your responsibilities, and all the things you have accomplished?
I'm not sure if there's ever um, a perfect balance.
Okay, that's cool.
Um, I'm not sure that that's possible. I feel like a lot of times you're giving up things to one degree or another. I, for me personally, I try to take at least a little bit of time every day to do something that's not chemistry related.
Okay.
I read a lot of nonfiction books that are not chemistry related.
Okay.
Um, and I personally, yeah, I read a lot of like memoirs and stuff like that.
Oh wow.
And so just having at least, no matter how busy the day is, how many hours I work, I come home, just do that one little thing that's not chemistry related. And
Mhm.
chemistry is great, but
Mhm.
if you're 24/7 every week, 52 weeks of the year, you're gonna just burn yourself out.
That is
So,
true. So, would you say compartmentalization is helping you to be balanced, or at least strive for balance?
oh, that's a good question as well. I'm also involved in a wind ensemble. That's a local wind ensemble. I play the flute, but we
Yeah,
haven't been able to do as much with COVID.
that's fair.
But in terms of compartmentalization, I do think it's helpful to at least have a rough idea of what you want to get done every day, and then week by week, thinking about what kind of goals you want to get to. And you won't necessarily make those goals every week. I know for this project, oh my goodness, so many weeks got pushed back because of small issues and things.
Okay.
But I also think it's important, more important than just like blocking out the time, is really being aware of how you work and what your signs of burnout are. So
Okay.
when I'm working in the lab during a day, there's a point in the evening, and I don't have a specific time or anything, but there's some point in the evening where I just feel like I'm on the verge to go home. And so I ask myself, I'm like, okay, what's our exit strategy for today? What things absolutely have to get done today? What things, if I still have things, can be pushed to tomorrow?
Hmm.
Because if I try to get through all of those things, I'll just be more burnt out for the next day. And so,
Okay.
kind of having that little check in at the evening just to figure out what I still have to do, um, can
Yeah.
be helpful in terms of making sure that I end at a place that I can kind of recharge and do those things outside of chemistry.
Oh wow, that's good. An exit strategy. I gotta write that down. Having an exit strategy, because I even with me, I don't, and I'm just starting, but even with me, you do have these goals of I want to complete this many reactions. I want to
Mhm.
purify this many reactions using the column chromatography, and I want to test this
Mhm.
much using NMR to confirm what I got. However, you don't always,
Mhm.
at least for me, I don't always achieve that. So,
Yeah. Yep.
yeah,
Yep.
yeah.
And I
So,
think also, you know, even as a fourth year, sometimes I still have trouble estimating how long it's going to take. I remember my first year, I always just like totally underestimated how long things would take me. And
yeah,
the issue with that is that you start to, hold yourself to these really unrealistic expectations. And
that's
that can
true.
be
That's true.
damaging if you
That could
continue
be.
to do that. But
That's true.
so I think kind of as you go with more practice, you get a sense
Hmm.
of how long things will take, and get a sense of um, your time in that sense.
Okay. Yeah, an evaluated experience does complement the progress and helps you learn.
Yeah.
Stana, I do have this question for you. I have two questions for you. Um, do you
Great.
have any advice to those wanting to pursue the field you are currently working in?
Ooh, this is a good question. For organic chemistry, I would say, if you're really passionate about the subject and you're really interested in studying it, um, continue to pursue it. Even so, like for me, I could have, well, I almost, there were a few stages in my undergrad where I seriously considered dropping out of chemistry altogether.
Oh wow.
Um, and there were moments that it was really hard to keep going, and
Yeah.
but I love the field of organic chemistry so much that
Hmm.
I was a little bit stubborn in that regard.
Oh yeah.
So I do
That's interesting
think,
that you say that.
yeah, I do think, if you're really interested in a field, go ahead and pursue it. And you might not have the most quote unquote traditional route to get there, but there's no one set way to get a career that you want to get, or kind of do the career goals that you want to do. And so, even if your path is untraditional, I would say, you know, don't feel like you have to hold that against yourself. There are times in my graduate program here that I've reflected on some of the benefits of struggling through organic chemistry and still pursuing this field, even though I didn't do well in the introductory courses as an undergraduate. I think it's helped me become a better teacher of the material. And there are definitely times where I think just kind of this untraditional background to get here
Hmm.
has allowed me to come and think about chemical challenges in ways that other people haven't, because they kind of, you know, perhaps went through the more traditional path.
Wow. So Stana, I like the word you use. You use the word stubborn. Interestingly enough, I interviewed a professor from MIT, and he used the same word to describe himself. He said, "I think it's just because I'm stubborn," and I think that's important because people phrase it differently. I persevere, or I hopefully I'm understanding this correctly, but I persevere, or I'm resilient, or even though resilient could be different in different situations, but um, it's good to be stubborn. It's good to have a goal, stick with it, and push through even when you have challenges. And interestingly enough, I think sometimes as we're going through these problems, sometimes the inkling or the idea comes to mind. Maybe I should switch. Maybe I should
Oh
transition
yeah.
out of this.
Mm-hmm.
However, I think
Oh yeah.
sticking with it, if that's something you're passionate about, I think that's still good. Yeah.
I agree. I agree. And the key is really, kind of facing yourself in the mirror and asking yourself, am I like, is this something I want to pursue? Because some people, um, it's tough to think about what they're passionate about, or they would like to be passionate about XYZ, but they maybe just like deep down aren't necessarily. So I think kind of asking yourself those hard questions. I've asked myself this many times, is this the field I want to be in? Is this a career I want to do? Um, so I think, along with kind of that persistence, being honest with yourself and confronting how you really feel deep down inside can be helpful.
That's good. Like I saw this book. I haven't read it yet, but it looks interesting. I saw this book on the library at home. It's called Self Confrontation. Yeah, that
Oh,
seems like
interesting. Yeah.
a good. Just like how you said, you have to confront yourself. You have to ask yourself these deep or these profound questions as to what my passion is. Is it something I can see myself doing for a
Hmm.
long period of time? And I think those will complement you, especially when it comes to professional schooling. So yeah.
Yeah, I also think that you shouldn't necessarily limit yourself either. It's really easy in the sciences to get stuck in these traditional preconceived paths for
Okay.
careers,
Okay.
when it doesn't necessarily have to be like that, especially if there are other things that you are also interested in. Um,
Mhm.
you can be interested in biology and be passionate about biology, but also have a successful career in like science journalism or something like that. And so, um, taking stock of what you're interested in, but then also being aware that there's not one stuck path where I choose biology and I have to do biology for the rest of my life.
Mm.
It's not like that. It might feel like that at times, but it's not like that. And
Mm.
so, um, being persistent, but also having an open mind, I think can be helpful too.
That's good. So, Stana, as we conclude, do you have any last words in terms of what is the most beneficial advice? If you had to sum it up in a few
Oh,
words, what is the most beneficial advice that you have received?
um, I think this is purely personal context,
Okay.
but for me, um, having the words, don't be so hard on yourself in the back of my head can really help. And I'm going to add one more, even though I said, I know you only said one. But the other thing is asking the question, what can I do? This is something I ask myself when I'm having a tough day in lab and I just don't want to do work, or I'm feeling like I don't belong here
Mm.
or that I'm not successful. I ask myself, what can I do in this moment to help move forward?
Okay, that's good. That's good, Stana. So, Stana, I really appreciate you taking the time out of your busy schedule to join me on this podcast. I wish you the best of the success in your future endeavors, and hopefully we may cross paths again as time progresses. Thank you again for joining me.
Thank you for having me.
Nobel Highlights Segment 2. The person we'll be focusing on today is the Nobel laureate of 1902, Emil Fischer. He lived from 1852 to 1919. Emil Hermann Fischer was born in Eukirchen, a small town near Bonn, Germany, on October 9, 1852. He died in Berlin on July 15, 1919. In 1902, he received the Nobel Prize for work on the carbohydrates and the purines. Emil Fischer's doctoral thesis reported on the chemistry of dyestuffs and colors. In 1862, August von Hofmann had prepared an important dye called rosaniline. The structure of the dye had been studied, but it was not known with certainty. In 1878, Emil Fischer, along with his cousin Otto, showed that rosaniline and related dyes were triphenylmethane derivatives. A little bit to note about his academic career. In 1871, Emil Fischer entered the University at Bonn, where he attended the lectures of August Kekulé and Rudolf Clausius. In the following year, he transferred to Strasbourg, where he studied chemistry with Adolf Bayer and earned his doctorate in 1874. He followed Bayer to Munich in 1875, where he became a Privatdozent in 1878 and a junior professor in 1879. He became professor and director of the Chemistry Institute at Erlangen in 1882 and took a similar position at Wurzburg in 1885. In 1892, he succeeded A.W. von Hofmann as director of the Chemistry Institute of Berlin. In 1888, Emil Fischer married Agnes Gerlach. She died after only 7 years of marriage. Together, they had 3 sons. 2 of the sons became medical doctors and died as soldiers in World War I. The third son, Hermann Fischer, became a distinguished biochemist and completed his career at the University of California, Berkeley, where he died on March 9, 1960. Indeed, a very good, excellent, great chemist. Functional groups and other ideas. Chemistry concept development 2. The key objectives for this discussion would be to understand what is a functional group, understand the key format for organic nomenclature, and understand the role of intermolecular forces. Functional groups are characteristic parts of molecules that convey specific chemical properties to the molecules that possess them. Functional groups do numerous things, but mainly they enable us to compartmentalize information about molecules, compounds, and reactions. Functional groups do give us insight into chemical interactions such as intermolecular interactions, as well as give us more information in understanding the properties of molecules. This includes the physical properties such as boiling points and melting points and solubilities. Considering the usefulness of functional groups, they also possess a characteristic molecular fingerprint that is detected in many ways, namely in spectra, which will be discussed in later episodes. Types of molecules and their properties. There are several types of molecules in the world. However, in the discipline of organic chemistry, there are specific molecules that are discussed frequently, including alkanes, otherwise known as paraffins, which are saturated hydrocarbons and aliphatic compounds. These molecules form a series of homologs with a repeating methylene, CH2, unit, and with the general formula CnH2n+2, and ending with the suffix -ane. For example, in increasing order from 1 to 5, methane, CH4, ethane, C2H6, propane, C3H8, butane, C4H9, pentane, C5H12. The following prefixes are hex, which corresponds with 6 carbons, hept, 7 carbons, oct, 8 carbons, non, 9 carbons, and dec, 10 carbons. These prefixes from meth to dec are applicable throughout the naming of organic compounds, alkanes, alkenes, alkynes, alcohols, etc. Moving on to alkenes, otherwise known as olefins. These are unsaturated hydrocarbons and they are considered aliphatic compounds. They contain at least one double bond, forming a homologous series with the formula CnH2n. These molecules end with the suffix -ene. As we progress, we discuss alkynes. Alkynes, otherwise known as acetylenes, are unsaturated compounds having a triple bond. These molecules form a homologous series with a general formula of CnH2n-2. These molecules end with the suffix "ene" or "ine", Y-N-E. There are several other molecules that form a homologous series within their groups, such as carboxylic acids and aldehydes. Now on to alcohols. Alcohols, whose main functional group for identification is the hydroxyl group, OH. It is notably priority in organic chemistry nomenclature practice. Exceptions include carboxylic acids, according to the International Union for Pure and Applied Chemistry. Alcohols contain one or more hydroxyls forming a homologous series. Alcohols are aliphatic, typically, and they typically end with the suffix "ol", OL. Now on to other ideas. Intermolecular forces and other properties. With functional groups come certain properties such as specific boiling points and melting points, as well as critical temperatures. The temperature around which a vapor is not easily undergoing a phase change to a liquid. So that's the definition of a critical temperature, and many other physical properties. However, beneath the surface of physical properties are the chemical features or interactions known as intermolecular forces, which influence and enable comparative predictions and physical properties. Namely, there are key forces to remember. Let's discuss dipole-dipole forces. These are forces which occur between molecules intermolecular with a dipole moment or a significant dielectric constant. These molecules are otherwise known as polar. These intermolecular forces, IMFs, are relatively strong. A relatively stronger version of this force is the hydrogen bond intermolecular force. Hydrogen bonding. Hydrogen bonding is a stronger force, sometimes referred to as a strong dipole-dipole force. This is a relatively strong, some consider it strongest of the IMFs. It occurs in water and other molecules with hydrogen bonds to nitrogen, oxygen, or fluorine. Moving on to ion dipole force. This occurs between ions and polar molecules, for example, with solvation of sodium chloride crystals in water. As we progress, we discuss London dispersion forces. London dispersion forces occur in all molecules and are based off of the Coulombic interactions between transient, in essence temporary, dipoles. These electrostatic forces result in transient interactions between molecules. Van der Waals forces. Now, a weaker force that consists of two kinds includes the van der Waals force, which is discussed in short here, and more elaboration can be found in other episodes. It is worth noting that IMFs and their strengths are based off of functional groups, chemical structure, and the types of chemical bonding in those molecules. You have chemical bonding, which can be subclassified into polar covalent bonding. Covalent bonding occurs between atoms with significant electronegativity differences. Specifically, this bonding occurs with heteroatoms, which refers to different non-metal atoms. Many times, the Pauling scale is invoked and used as a reference for ranges to determine the type of bonding arrangement occurring between atoms. If bonding, though considered a theoretical construct in some cases, is viewed on a spectrum, polar covalent bonding would exist around the middle. Covalent bonding. This is almost another end of the bonding spectrum where there is a less significant difference in electronegativity. Of course, significant in some cases is debated. Ionic. This at the other end of the bonding spectrum. This occurs between metals and non-metals. For example, in sodium chloride, there is a large difference in electronegativity. Solvation. Solvation is dependent on many factors, including the principle like dissolves like, and ideas such as hydrophilicity and hydrophobicity. Now, as we discuss hydrophobicity and hydrophilicity, these terms refer to molecules and their stance in relation to water. If it has a significant affinity for water, it is hydrophilic or water-loving, or less significant affinity for water, hydrophobic or water-hating. The tendency of molecules is as follows. Polar and ionic compounds tend to be hydrophilic compared to covalent and non-polar compounds, which tend to be hydrophobic. Now, molecules that possess both hydrophilic and hydrophobic properties are in many instances considered amphipathic. Now, nomenclature in a nutshell. Nomenclature, according to IUPAC, is based off of four main parts: the prefix, the locant, the parent chain, the suffix. The prefix normally refers to the number of each substituent or functional group attachment. Prefixes include di, tri, tetra. The locant, which is the number that describes the functional group attachment or the substituent's position. The parent chain, this is normally the longest continuous chain in the molecule. The suffix, this is based off of the presiding or prioritized functional group, chain, or bonding arrangement. Suffixes are typically classical in ending, with "-ane" for alkanes, "-ene" for alkenes, "-ine" for alkynes, "-amine" for amines, "-amide" for amides, "-oic" for carboxylic acids, "-ate" for esters, "-one" for ketone, and "-dehyde" for aldehydes. Key fact to note: the alcohol's functional group hydroxyl, OH, is normally prioritized overall. Substituents are transcribed or outlined in the name based on the relative alphabetical order, so ethyl before methyl, and that pattern continues. The key overall idea in nomenclature generally is we follow the guideposts of prefix, locant, parent chain, then suffix. As we progress, another key concept to note would be selectivity, which in reactions within the context of organic chemistry typically describes which product is favored, and specificity, which typically refers to what is mechanistically allowed to occur or to form. You have chemoselectivity, which typically refers to the functional group that's going to be reacted on. Regioselectivity, in which cases we look at which part of the functional group will be reacted on. And stereoselectivity, which explains how it reacts or what 3D conformation of the molecule is formed in the reaction. These are the key concepts for this segment. Thanks for listening. We're glad you were able to tune into this podcast. Once again, this is The New Chemist, where we discuss chemistry, which simply put is the science of change, as well as the other sciences, careers, community, research, and COVID-19. Thanks again for listening. Note, the views on this podcast represent those of my guests and I.